Okay, I hope I can be heard and my slides I've seen.
The slide is not in full screen mode yet, but otherwise everything is perfect. We see you, we hear you.
Oops. Sorry, now I'm using a different. Okay, so sorry for being left over. Thank you, Uli, for introduction, and maybe most of all, I would like to thank the organizers for nice invitation. But I have the pleasure to close the workshop, and I think it was, even without my presentation, it was nice. I think everybody can agree on that. I will be quite short, I think. I would like to present the paper which was written with Wojtek, but it was motivated actually by the discussions with the NA61 Shine collaboration with Gaździcki and collaborators. And actually, the idea is simple. So actually, I'm a bit afraid that I'm talking about two simple things here, but let's go. So
don't worry.
So basically, the motivation I could easily skip after Friday's talks. We are motivated basically by the idea that if there is some orbital angular momentum, which is quite large according to some, let's say, approximate calculations, if there is some mechanism which can transfer this to the spin, actually this angular momentum should be seen in the final emitted particles at the free zone. And in particular, this can be the case for any particle which has some spin, but we are focusing on lambda. Now, this was actually measured not so quite long ago, in 2017, although the first measurement was much earlier in 2007. But finally, it was detected that the effect is on the order of couple percent, but it's measurable, and I think it's amazing result in some sense. And it was it got lots of interest among all of us. Now, in order to measure this effect, what is used, actually, we employ the fact that actually there is preferential emission of the daughter proton in the lambda rest frame decay along its polarization vector. Now, for that purpose, we use the law for the emission in the angle, and it basically, in the lambda rest frame, depends on the dot product of the polarization of the mother lambda and the daughter proton. Now, what got our interest actually was this particular plot, and this plot was given in the first paper of STAR. And why it brought our interest, because basically what you see here is something weird in some sense, because you see the emitted proton momentum and the angle theta star, which actually is plotted between the emitted proton and the global orbital angular momentum. So basically, you are what is star plotting here is they are showing basically the angle between lambda rest frame quantity and the quantity angular momentum which is given without the star. So it's given in the center of mass frame. So this was kind of, this brought our interest, because this is something which is not really in agreement with relativity, right? If we go to if we assume that the particles are quite relativistic, let's say we take the lambda of the highest, I think, 4 GeV momentum, then actually this L, so this orbital angular momentum will be pointing in a different direction. So it actually should be transformed. Now, so basically what we do, we just take the usual orientation of the coordinate system, and then we find that our angular momentum should point into negative direction oppositely to the y direction. And now on the right hand side, we see what happens in the center of mass frame, assuming that reaction plane is here 0. One can include this, but for simplicity, we just take it 0. We assume that the experimentalists can detect it very well. So basically, you have the emitted lambda momentum. And what you do now, you transform to the lambda rest frame. So you take the canonical boost. This is actually composed of 2 rotations, boost along z direction, and then inverse 2 rotations. And then you can check easily that you land with the reference frame where your lambda is at rest. Now what you do, you should look at what happens with the orbital angular momentum. And then we expect that spin part is 0 at the very early stage. And what happens with the orbital part? Basically, orbital part transforms here as spatial components of the antisymmetric tensor. So it basically transforms as elements of the something like Faraday tensor. So you go to the book by Jackson, you take the transformation law for the Faraday tensor, and particularly the magnetic-like components. And you find that actually in the S prime, now I will use 2 different frames. S prime is the frame where we just go there with the canonical boost. And then you will see that actually transformed vector, the orbital vector will, angular momentum vector will point in a different direction due to the relativistic correction. And of course, the more relativistic particles, the different the direction will be. And actually, it's dependent also on the actual components and not only on the magnitude. Well, let's see how this affects our orbital angular momentum in practice. So if you take now that we take the normal vector pointing along orbital angular momentum, and it's pointing in the y direction, negative y direction, the boost part should be 0 actually, and this should be easily proven if you are in the center of mass frame. And then you take basically the canonical boost, and then you land in the lambda rest frame. Well, the components transform somehow not really beautifully, but you can see on the left-hand side in the 2 plots how the new orientation of the orbital part would look like. So as expected, if the particles are not really too fast, all the orientations are basically along the y direction. But on the right hand side, if you take like lambdas of the order of 4 GeV, then actually the orientation is quite different depending on the values of the lambda velocity in y, z, and x directions. Okay, so now I don't have too many slides, but let's now check how this would affect the measurement, because we just saw that this indeed affects the orientation, but how this would affect the actual measurement, we don't yet know. So actually, it's quite useful to introduce one one more rest frame, and this is a frame where actually we do 2 more rotations, but these rotations are done in such a way so that we land with the new frame that z direction points exactly along the polarization vector of the lambda. So basically, the theta, the polar angle would just be the angle between the proton in the So basically, if you go do the new frame, you will see that also your proton momentum will transform somehow in a very complicated but simple way. You just apply this rotation to the momentum of the proton, and actually now you will find that indeed the star pz component of the proton is exactly the one that enters the lambda weak decay law. So now you see that this dot product can be given entirely as a cosine theta star. So this is the z component angle in this rotated lambda rest frame. Now, if you go back to the primed, so the frame which is just connected by the canonical boost with the center of mass frame, this will be just exchanged with this part pz, which is expressed in terms of this rotation. So how the momentum is oriented is connected with the actual orientation of the polarization vector of lambda. Now what you do, you basically average this lambda weak decay law, and with the momenta of the emitted particles, of the emitted protons, and you will see that actually averages in the lambda rest frame of the emitted protons will give you exactly. So if you would perform all the averages of z, x, y components of the emitted protons, you exactly reproduce. You would be able to measure the polarization vector of the lambda as given in the lambda rest frame connected with the center of mass frame by just the canonical boost. Now, but what does the star do? The star actually does not the following thing. They average the sine phi of the proton emitted in the lambda rest frame, and then if you interpret this this kind of weird part with the pH, so you will get exactly what is given in the papers by star collaboration, and then if you look back and at the parametrization of the polarization vector of the lambda in its rest frame, you will see that this is exactly the y component. So what they do, they measure the y component of the polarization vector of the lambda. Now, of course, this is not really the component of the polarization vector along the total angular momentum, because as I showed in the previous slides, it's different if you go to the lambda rest frame for each lambda with different momenta. So basically, if you would like to average over different lambdas with different momentas, then you would have to transform this vector for each momenta separately. Of course, it is also tempting to measure the cosine phi component, and that would give you the other x component of the polarization vector, and actually the ratio would give you the angle capital phi prime. Now, the last thing is the question, what can be done better? Better could be done is the following. So if we have the polarization, let's say, and we are able to measure the averages of the emitted protons, momenta, we could actually use the transformed orientation of the orbital angular momentum and calculate the dot product. We just project the polarization on this direction, and then we should average over lambdas. Why this is different? Because, as I said, for each lambda of each different momenta, this direction and this dot product will be different. Now, last thing, numerical estimate. Okay, maybe all of this, what we are talking about, doesn't really matter in practice. Let's orient now our polarization vector along the orbital angular momentum. So let's assume that it's pointing exactly in the same direction. And then by calculating the dot product, we would expect that actually it should give 1. But so what we do, we calculate the projection, and then we average over the lambdas of different momenta in a certain range between m and n GeV, with the lambda given by this kind of equilibrium distribution. We took the effective temperature of the order of 150 MeV, and what you get, you basically have the following numbers, which are given in the bottom left corner. You see that basically for very low, slow part lambdas between 2 and 3, this is indeed small correction. This is correction on the order of 3%. For very energetic ones, it can reach up to 10%. Now, of course, if you would take only lambdas of certain momenta, you would just have to include that there is additional correction or an error, some uncertainty connected with the systematic uncertainty connected with the possible different orientation of the orbital angular momentum. But if you mix lambdas with different momentas, then you have to be careful, because if you are going to mix them in different portions, then of course you are having some uncontrolled difference. So this is all what I wanted to talk about today. We just looked what actually how the measurement is done and what is the theoretical interpretation of actually the measurement done by Star and also by Alice. We have shown that actually there is another way to perform this measurement, but this is up to let's say experimentalists whether such measurement is possible or feasible due to some well, this is up to technicalities, I guess. And we showed that this correction may be up to 10%. So thank you very much.
Thank you very much, Radek. You left us with plenty of time for questions and discussion.
No
Unfortunately,
problem.
some of the people who were yesterday the main actors in that session on lambdas are not online, but still, let's ask for questions. And maybe while I'm waiting for hands going up, let me ask a question myself. Which direction does your effect go? In other words, if you, in your mind, corrected the analysis done by Star in the way you would like to see it, would the polarization signal go up or go down?
Well, it should go actually down because of this results where I showed here.
So you're saying that overall the polarization is overestimated by an effect of the order of a couple of %. But if you look at the high momentum lambdas, the polarization might be overestimated by 10%.
Yes, but I think I hope that people will take this message correctly and don't take this as a criticism. It's just the way that we started trying to understand how this is actually done, because somehow we all like this beautiful plots and interpretation, then we can really connect final state with the initial state and have some interpretation in terms of rotating systems. Of course, this doesn't look like this. It's taking, it's happening on the local, let's say, locally, but somehow we would like to connect this to these two effects. And in my opinion, if one takes actually mixes different lambdas with different momentas in the measurement, then I don't know how this could affect. You also go for different from high energies to low energies, and then maybe the portions are differing. So yeah, so this is something which may be only addressed probably by the experimentalists.
But it's not, it's something they can do, right? I mean, they are measuring the momentum, right? It's just isn't it? Do I misunderstand? I mean, it's something you're just saying they measure the momentum.
No. So this is so what they the whole thing was I tried to explain in this slide, because what we would actually like to do is in the right lower corner. So we would like to actually measure all three averages of the momenta for lambdas, and that would exactly give us for certain lambdas of certain momenta, if we average over many of them, it would exactly give us the entire polarization vector. But this is not what is done. It's done the second slide. So they just averaged over this sign and they just get one component of this polarization. This is first thing. The other thing is that probably they do this because of some resolution or effectiveness of the measurement. Maybe just they are optimized, their tools optimized with respect to averaging of sine and cosine. In particular, they don't measure the cosine, they just measure the sine. But yeah, so but somehow when we tried to somehow discuss this issue with who was the guy? I just lost the name. However, the guy who was responsible actually for this measurement in
Isaac.
Yuri.
Yuri is a theorist, right?
Sorry.
Did you mean Isaac?
I can give you no, not Isaac. Actually, we didn't have the opportunity to discuss with Isaac, but I will give you the name immediately. So basically, sorry, I don't have. Yeah, Selyuzhenkov, Ilya Selyuzhenkov. So he was actually very interested in doing this measurement for Na61, although it's much more complicated at Na61, because Na61 actually has complicated magnetic field in the TPC, and this is somehow, I don't know if they even have the TPC, but somehow in the emission region they have huge magnetic field, and we were trying to understand how this magnetic field can actually go over on top of the measurement itself. But it seems it's doable actually, but it's more complicated. But I think they have not been able to explain why they cannot actually do just the averaging of the momenta. I'm actually sad that I was not able to give this talk yesterday on Friday.
All right. Sometimes technology doesn't help. All right. So I think we should thank you again for your talk.
Thank you.
Even if somewhat belated, it was an interesting thing to be aware of and keep up following up. We are entering a session